So in this video, we want to introduce what is called the fundamental counting principle. Very basic. Sometimes books might call it the multiplication rule or the multiplication counting principle. But this rule is used so often in probability, which is where we're going later on down the road, that it's important to bring it up now. So if an event consists of k steps, and step 1 can occur in n1 ways, step 2 can occur in n2 ways, etc., then the total number of possible outcomes is simply the product n1, n2, all the way out to nk. And so you can see why it's sometimes called the multiplication rule or the fundamental counting principle. So let's do this example. We'll skip around and not necessarily do every single one. But these are very straightforward. How many lunches can be ordered from a menu? 3 appetizers, 4 entrees, 2 desserts. So it's very straightforward. We first select our appetizer. That's 3 choices. And then we select our entree from 4 choices. And then we select our dessert from 2 choices. And I simply compute the product of these, which comes out to be 24. Let's take a look at C. The classic board game Clue consists of 6 suspects, 9 murdered weapons, 9 locations. How many different outcomes of suspect, weapon, location can be constructed? Okay, so for those of you who are familiar with the board game Clue, you randomly select a suspect in confidence and put them in a sealed envelope, followed by a murder weapon, followed by a location. So there are simply 6 suspects. There are 6 different ways that event can happen, 9 different potential weapons, and 9 different locations. I now wish to compute the product of these, which is 486, which simply means there's 486 different possible suspect, weapon, location outcomes per se when you play Clue. Let's take a look at E. We'll slide down here. Like I said, we're going to skip around on some of these. 3 fair-sided dice are rolled. How many different outcomes are possible? Okay, so I'm rolling 3 6-sided dice. So when I roll the first die, there are 6 different outcomes that could come up. When I roll the second die, there are 6 different outcomes. And for the third die, 6 different outcomes. And I simply take the product, which is 6 to the 3rd power, or 216. Human blood is of 4 different types and 2 different RH factors. How many different blood types are there? Okay, so there are 4 different types. There are 2 different factors. By the way, the types are A, B, AB, and O. And the RH factor is either plus or minus. So 4 ways for the first event, 2 for the second, for a total of 8 different outcomes. Let's take a look at G. The Braille system uses a 3x2 block with a dot either present or absent from each of the 6 slots, where there must be at least 1 dot in one of the locations, meaning we cannot have all the slots blank. How many different Braille characters can be constructed? And just a little FYI right here. If all of the 6 dots are empty, meaning no dots at all, that implies a word space. That signals the visually impaired person that there's a start of a new word. So let's see how this is constructed. If you're familiar with what Braille might look like, it's a 3x2 block. And each of these, a dot is either present or it is absent, more or less, okay? I either put something in the spot or I don't. And so I wish to simply attempt to compute how many different characters can be constructed. So there are 2 different choices for this first spot. I either put a dot or I don't. It's either present or absent. For this second slot, there are two different choices. There's either a dot present or there's not. And so if you see the pattern, there's simply two choices for each of these 6 slots on my Braille character. The dot is either present or it is absent. And so I compute the product of all of these, which is 2 to the 6th, which is 64. Okay? Now, included in this, though, is the Braille character where no dots are present, which simply means a word space, and that is 1 of the 64. So how many different characters can be made? Well, that's simply 64 minus 1, so 63 possible characters can be made. I'm going to skip H and move into a new definition. Okay. Suppose x1, x2 out to xk are sets, and the ith set has the ith set xi has n sub I elements. If x1 to xk are pairwise disjoint, what pairwise disjoint means is it means every intersection of two different sets is the empty set. So x1 has nothing in common with x2, nothing in common with x3, nothing in common with xk. Okay, so each of these sets are pairwise disjoint. Then the number of possible elements that can be selected from x1 or x2 or xk is simply n1 plus n2 all the way out to nk. So let us see if we can't use this with what we've already discussed to answer a question. How many ways can we select 2 books from different subjects among 4 math, 6 history, and 3 art? Okay, so I have math, history, and art. Okay. And I'm simply going to call math set x1. Now, how many different math books are there? Well, 4. So the size of x1 is 4. History, we'll call this x2. How many different history books are there? That would be 6. Okay. And art, we'll call this x3. So the size of x3 would be 3. Okay. Now, each of these are pairwise disjoint, meaning a math book's a math book. It's not math and history. It's one or the other. All, how many books do we have right here? 4 plus 6 plus 3. All 13 of these books are only classified as one and only one, either math, history, or art. So, first, let's find out, or read this right here, the fact that I need 2 books from different subjects. Okay, so I could get math or history, okay? And that is simply x1 union x2. Okay? Well, there are 4 ways that I could select a math book times 6 ways that I could select a history book, so 24 maths or histories. Well, what else could I get? I could get a history or an art. That is simply x2 union x3. Well, how can that happen? That is simply 6 times 3, which is 18. And there's one other case that we haven't explored. I could get math or art. That is x1 or x3, which is 4 times 3, which would be 12. Now, what our definition says is that I wish to add all of these right here. So if we go 24 plus 18 plus 12, I get a total of 54, meaning there are 54 different ways that I can select 2 books, and those 2 books will be from different subjects. Okay? Let's move on and take a look at this table right here, and let's consider rolling a pair of dice and computing the sum. So I've got a pair of dice, so die 1, 1 through 6, die 2, 1 through 6. I'm going to roll these dice and I'm going to compute the sum. That's often what we do when we roll a pair of dice. And so what I'm going to fill in the body of this chart right here is very basic. If I roll a 1 and a 1, the sum is a 2. A 1 and a 2, the sum is a 3. A 1 and a 3, the sum is a 4, 5, 6, 7. A 2 and a 1 is a 3, 4, and we can just fill the rest of this chart in pretty easily. 4 and a 1, 5, 6, 7, 8, 9, 10. 5 and a 1 gives me 6, 7, 8, 9, 10, and 11. And a 6 and a 1 gives me a 7, 8, 9, 10, 11, and for those of you who know, the maximum sum when I roll a pair of dice is 12 if I get a 6 and a 6. So let's ask a couple of questions. How many total outcomes exist? Well, this is the fundamental counting rule. Very straightforward. 6 ways to roll the first die, 6 ways to roll the second die for a total of 36 outcomes. Okay, how many ways could one roll a sum of 7? Okay, well, that occurs 1, 2, 3, 4, 5, 6. So there are 6 ways to roll a sum of 7. Okay, how many ways could one roll doubles? And when we say doubles, that simply means we get a 1 and a 1, a 2 and a 2, etc. So the same number on each die. So that would be this diagonal right here. A 1 and a 1, a 2 and a 2, a 3 and a 3, a 4 and a 4, a 5 and a 5, a 6 and a 6. And there are 6 ways to roll doubles. Which sums are least likely to be rolled? Well, I simply look in the table right here, and I notice that rolling a sum of 2 only happens one way, or one time, and rolling a sum of 12 only happens one way. And so we'll say simply a sum of 2 and a sum of 12. Rolling a pair of die, very important to understand various probabilities when I roll a pair of dice. Let's take a look at one more example. Suppose a fair coin is flipped thrice. Construct a tree diagram and list the possible outcomes for the 3 tosses. Okay, so I have a fair coin, and the fair coin can pop up either heads or tails. Okay? And it's important to notice that I'm flipping this n equals 3 times. And we're going to construct what's called a tree diagram. Now, as we progress through the course, when we get into the last unit and we begin graph theory, you'll see why we would call this a tree diagram. So, very straightforward. On the first coin flip, the outcome could be H or T. And that lists the 2 outcomes if I were to only flip the coin once. However, I'm flipping it thrice. So if the first outcome was a heads and I flip it again, then I could get a heads or a tails. Or if the first outcome was a tails and I flip it again, I could get yet again a heads or a tails. And so I just continue this tree, more or less, and we'll define what a tree is later in a mathematical setting when we discuss graph theory. But I continue to do this for the number of flips, and I'm going to do it one more time because I flipped the coin thrice. And the beauty of this then is that each route in the tree, describes one of the possible outcomes that we could observe. So let's quickly list those. It's not difficult. I could get H, H, H. I could get H, H, T. I could get H, T, H, H, T, 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 H, H. That's this one. T, H, T. T, T, H. And lastly, TTT. Now, this shouldn't come as a shocker. Let's count how many outcomes there are. That's 1, 2, 3, 4, 5, 6, 7, 8. N equals 8 items in what I'm going to eventually call the sample space. But this shouldn't come as a shocker as to why it's 8. When I flip the coin once, there are 2 different outcomes, heads or tails. When I flip the coin a second time, there are 2 different outcomes, heads or tails. And when I flip the coin the third time, 2 different outcomes, heads or tails. The fundamental counting rule says take the product of these 3, that is 2 to the third power or 8. So there we have it.